Okay, it's really my great pleasure to introduce, Hervé Delingette. He has been contributing to our scientific community since end of 80s. He looks much younger than that, but he has been he's much longer in this community. He actually did his degrees, including the PhD in engineering at École Centrale de Paris. And then he spent 3 years in Carnegie Mellon University doing research on robotics at end of 80s, early 90s. His career was in the prestigious INRIA, Institut National de Recherche en Informatique and Automatique, and where he's currently a director of research. He has got many awards in his career, many of them, and I can just mention a few of them. He got the Laval Virtual Award of Medical Section already in 1999. He got the Dirk Bart's Prize at Eurographics in 2015, the Arts Award by Apple Incorporation for CardioSense 3D project. He got many Best Paper Awards, including, Mika Young Investigator Awards that he supervised, FIMH, IEEE EMBS, Best Paper Award at IEEE Robotic and Automation. He has over 20,000 citations. He has been actually one of the lead researchers in our community, and now he is also chairing the AI Institute of at Côte d'Azur, and he is also a member of board of MICAI Society and a fellow of the MICAI Society. It's really a great honor and pleasure for us to have Hervé Delingette giving this invited talk. Thank you very much, Hervé, for
thank you. It's my pleasure.
And looking forward to listen to your talk. Okay.
So thank you very much for inviting me in this prestigious lecture series at TUM. And so I will start sharing my screen and hopefully. So I chose as a background an unusual view of Nice. That's what I was expecting. It's you don't see the Mediterranean Sea, but it's the public library in Nice, where you see the head with a square, la tête au carré en français. And this said, I will talk today about a topic related to annotations in medical image analysis. Since it is a central topic that comes in various occasions as soon as you perform the analysis of medical images nowadays. So just as an introduction, I will introduce the notion of annotation. So this is any additional information that is provided by an expert on an image. And this type of annotation can be points in the image or landmarks. It can be also text or labels, which can be attached to an image, to the whole image, to a slice, or to a landmark. And I'm here citing a famous labels from a Belgian painter. It can be also a region of interest, like a bounding box in 2D or 3D, and a very rich type of annotation is, of course, a segmentation mask. So those annotation, usually, they can be useful for two types of application. The first one is for the supervision of machine learning algorithms. So in this case, the the annotations are used in the training set. And the second use of those annotations can be also to assess the performance of the algorithms, in which case they are used in the testing sets. But an important specificity of our field compared to computer vision I would say, is that the annotations of associated with medical images are of high costs. And the reasons are that, first of all, the medical images or medical data are heavily regulated, which means that the access to the data itself is very complex. And if you want to do the annotations of large databases of medical images, for instance, you need to deploy a fairly sophisticated image annotation software. So the example of that is the OHIF initiatives, which is a web-based applications where you can access, visualize images remotely, and also add annotations. And there are also a number of commercial solutions like Diplomatic or Incepto. These are mostly French startups, but there are also a number of commercial solutions that already exist. So it's hard to access to the data, so therefore it's hard also to produce the annotations. Also, producing high quality annotations is difficult and time consuming. So one aspect is that we are mainly dealing with volumetric images with many slices, and also the fact that the exploration of the data, it takes time and is complicated. And finally, the number of highly trained raters, which are medical doctors, is limited. And this is why, for instance, we cannot use solutions like crowdsourcing, which are used in computer vision, or at least it's not impossible, but it's difficult to use it in our field. And the cost of accessing raters ranges from $10 to $1,000 per hour. So the cost is not only in terms of time, but also in terms of money, of course. So on top of that, the annotations are ambiguous. So the first reason for ambiguity is the intra and inter-rater variability. So what you see on the top right is a T2 weighted MR image of a prostate, where 5 raters have outlined the whole gland, the prostate. And you see that there is a fair, of course, I have chosen the slice where there is a large disagreement, but you can see the extent of disagreements among the raters, and I should say that those are all radiologists. So there is this ambiguity, and a part of this ambiguity is related to the annotation protocol. Of course, this is a very important aspect. If you want to decrease the variability among raters, you need to specify very clearly the protocol for annotations, where you start, so where you end. And so you need to have warm-up sessions and training sessions before you can actually collect the annotations. And this was the case in the image produced here, where all 5 raters were actually trained, and the protocol was set up fairly carefully. And finally, another source of ambiguity is the annotation tool. So for instance, if you want to outline the prostate in this image, and using the same software like Made in RIA here, which is an open source software for visualizing and annotating images. So whether you are using a brush tool, so a brush tool is where you add pixel per pixels regions. And on the right-hand side, you see a polygon region of interest tool, where you define a spline, 2D spline that you can propagate in space. So depending on which tool you use, of course, the contour will be either smooth, if you are using the spline-based representation, or much more jaggy and potentially more accurate on the left-hand side. So all those facts creates some variability in the data and ambiguity. So therefore, not only you need, it's costly to acquire, but you need many of them to have a reliable information. So now I'd like to just provide a main pipeline used in medical imaging, where you start collecting image data. here, for instance, cardiac MR and CT. Then you start collecting image annotations. So they can be, again, various type of annotations, strong annotations, such as the delineation here you see in this image, or it can be labels, which are weak annotations. And finally, you are designing your AI algorithms in order to solve the task that you are interested in. So this is a very common pipeline. And my lecture today will concern two of those stages. The first stage, so yeah, we have a problem of coping with limited and uncertain annotations. So the first stage is what is often called nowadays data-centric AI, which is working on the data itself and the annotations first, because this is an important source of performance. So in this case, in data-centric AI, the two problems I will discuss will be the quality assessment of segmentations and segmentation mask in particular. And the second problem is how to fuse the data annotations. So this is again the first part of this, let's say, analysis, which is centered on data. And of course, the second part is model-centric AI, which is more into improving the algorithms. And I will focus mostly on mixed supervision, and then the concept of mixed supervision, and then I will list at the end of the presentation some concepts also related to the main problem that I outlined before, which is how to cope with limited annotations and their ambiguity. So I will start with the first topic, again on data-centric AI, which is the quality assessment of segmentation mask. So first of all, I would like to provide just a general concept. So in medical imaging, we can state that we are in the regime of small data. And because the number of images, despite the fact that you have many slices, we are talking about volumetric images in most of the cases. So despite the fact that you have a lot of different slices, the number of patients is fairly limited. So the largest database I know of consists of thousands of images, but we're not talking about millions of images so far. So therefore, and most of the database available right now are more in the hundreds. So we are in the small data regime, and in this regime, it is very important to get a noisy to avoid having noisy labels, because this can have a large impact on the outputs of your trained algorithms. So this is in opposition to having a big data, where you can actually cope with noisy labels due to the amount of basically data that are similar to each other, and where you can actually naturally, without any additional action, you can actually naturally average the noisy labels into reliable ones. So this is why I think it's important that we are able to curate the annotations, and we'd like to reach this small data with clean labels objective. So this will be illustrated first of all into this problem of segmentation mask. So there are a number of databases where we have segmentation mask available. So here I cite the BRATS 2017 datasets with 200 plus MRI scans of a head, of a brain. And also we used computer vision images. Here, the COCO dataset with 5,000 real-world images and 80 object categories that has been outlined. So the question is the following: can we actually detect or assess the quality of annotations? In this case, the quality of segmentation masks that are provided by the experts. So we'd like to do this but without any supervision. So of course we can ask another expert to look at the annotations done by the first experts and then to reach a consensus. But then you could also, you know, it's a famous saying, who will guard the guards? And so we'd like to do this in a very data-driven way without any supervision. So I provide here this example from the BRADS dataset. So you have for instance, the two leftmost segmentations of a BRADS tumor here. They are, I think they are easy to understand from the user point of view. However, the one on the right is questionable. So the problem is that we can ask ourselves whether it's the fact that you are not outlining the white lesions, the white signals. Is it due to error from the writer, or is it actually the fact that the writer takes into account some anatomy information that is not in the image? So we can ask ourselves, so should we supervise again these segmentations and question it and ask some revision of this annotation? So the objective here is to perform some automatic triage of the segmentation mask and to do this in a fully automated way. So for this, our idea that was developed into these papers was to say, okay, we have no ground truth, of course, so there has been a quality control algorithm performed in the past by several authors, and usually these are supervised. So they use some gold standard, some data set where they are absolutely sure, and then they use this in order to monitor the segmentations from other writers. So here we do this in a fully unsupervised way. And our approach is the following. We compare the input segmentations with the simple data-driven segmentation model. And then we detect the cases with large discrepancy. So to illustrate this, we start with the segmentation provided by the manual writer. We provide, so this is segmentation S, we provide a probabilistic segmentation that are in green here. We measure somewhat the distance. And then we do this for the whole data set, all data in data sets. So we end up with a histogram of distances. And then we can look at the right tail of this histogram for images that are suspicious of being with low quality annotations. So more precisely, for the probabilistic model, we use we combine an intensity model based on a mixture of student T distributions. So we use parametric distributions in order to get something more robust, and we use a mixture of the student T, which are a generalization of Gaussian distributions. So this is, we use a mixture both for foreground and background. And then we add also some prior label model. And in this case, we do not use a Markov random fields because we want to estimate all parameters of a model. So we are in a fully data-driven approach. It has to be, again, without any hyperparameter. And so we develop this generalized linear label prior based on Gaussian process, but also we can use a combination of Gaussian basis in order to enforce the smoothness of a recovered contour. So just an example of that. So this is the input from the BRADS image. Here we get the input segmentation from the rater. We devise some narrowband, and from that we automatically extract the probabilistic model. Actually, the probabilistic model could leak outside the narrowband. This is why we use the narrowband to constrain the extent of these posterior segmentations. And once we have this, again, we can compare. We can compute this distance and then draw an histogram. So this is an example for the BRADS 2017 dataset. So where on the right-hand side here, you can see that you get images and segmentation that are well explained by the probabilistic model. So the hypothesis of a probabilistic model is simply that you have a change of appearance between the foreground and the background, and that the border is rather smooth. So these are the hypotheses behind this. And so this is what you get on the left-hand side. On the right-hand side, you get on the bright data set, for instance, this segmentation. So you see the red contour is the ground truth, while the yellow one is the probabilistic contour. And you can see that the rater was using some thresholding, and that he proposed this to be the glioma. And in fact, when we came back to Bjorn, actually Bjorn Menzer, who is came back with this this database, he agreed that this was a very suspicious and probably a low quality segmentation. But that was provided to all users of BRAS datasets. So this is an example of, let's say, suspicious and dubious annotations that are provided in these datasets, and but which is also used for training, but also it's used for testing. It's used to assess the quality of segmentations, and in this case, it's a problem because the quality of this reference segmentation is low. Another use of these algorithms is also to assess the quality of a model performance of large databases. So here, this is a work on CT images, where actually we developed an algorithm to segment the cochlea. So the cochlea from CT images of inner ear. And in this case, we apply it on 1,000 CT images. And we had, of course, no way to assess the quality segmentations because the manual segmentation of this cochlea is extremely time-consuming. And this is because the cochlea has a very specific shape, and it takes a lot of time, and even the quality given by the radiologist you need a lot of time to reach a reasonable quality of manual segmentation. So what we did is that we used the unsupervised approach to monitor again the distance between the output of the algorithm. So this is the 1,000 segmentations. This time it was provided by an algorithm, not by a rater. And then we sampled 5 different images, only 5 images, where we asked a manual rater to segment the structure. And from that, we could actually see, but this is investable, but there is a good correlation between the distance between the probabilistic model and the output of the segmentation. So you see this distance here with increasing distance. And then with the dice score. So if you have a high distance, like this one here, you have a low dice score. While if you have on the left, you have a low distance but a high dice score. So and this way, we used this to have a probabilistic estimation. It's basically a Monte Carlo sampling for assessing the quality of the algorithms, because it's absolutely out of reach to segment 1,000 images. But by sampling according to this distance, we can provide an idea of a dice score of the whole data set. Okay, now I will switch to the second topic on data-centric AI, which is related to the fusion of data annotations. So this has also to do with segmentation mask. And usually, again, the segmentation masks are used to assess the quality of especially the segmentation algorithm. So in the classical way, you consider your manual segmentation to be a ground truth, and then you have the algorithm performance, and then you measure the distance between the ground truth here and your algorithm performance here. And therefore, you use a metric. Typically, it's a dice, Hausdorff distance, any metric, which basically measure this distance. The problem, in fact, is, as I said already, is that there is actually the annotations is noisy. So in fact, the typical situation is more like this one, where you have multiple targets, and then you have the output of your algorithms, like here. And the problem is, how do you assess the performance of an algorithm given that you are dealing with with the distribution of ground truth segmentations? And so one way of doing this is to estimate. But it's only one way to estimate the consensus among the different raters outputs, and then to use a distance between now the consensus here and the algorithm performance as previously done. This is one way to basically summarize a distribution with a single point. So this is, of course, assuming that you have a single mode distribution. So one example of that is, this is what we've done also on the prostate segmentation from MRI, T2 weighted, where we train neural networks to segment first. We localize the prostate into this image, and then we segment the whole gland, but also the peripheral zone and the transition zone of a prostate. Now, I will not enter the details of the method, but I will just show the comparison. We compare the algorithm with 7 experts. So the 7 experts were radiologists with various experience. And then we use the consensus of the 7 segmentations, both for the whole gland and the peripheral zone. So we use this as a reference, and then we compare the distance between each raters with respect to the neural net. So the red arrow points to the performance of the algorithm, the networks, and then we could see that basically the performance of a network was average compared to the 7 experts, ranking between 3 and 4 among the 7 experts. So this is basically one of the few examples where we really have a good assessment of inter-rater variability in order to assess the performance of the algorithms. Now, the topic I will now discuss is how do you estimate this consensus? Basically outlining 2 types of challenges. The first challenge is that the rater, actually, the performance of a rater may not be, let's say, the same for the whole structure. So the classical hypothesis for the previous work is that each rater has a single performance, meaning that for every part of a structure, the performance of the rater is the same. So in our case, we relax this hypothesis where the performance of an outlying structure can vary spatially. And the second also hypothesis that we relaxed is the hypothesis that there is a single consensus. So, and I will just go through this more maybe faster than I planned, because time is moving on. So first of all, just to show the problem of robustness also. So here you have 3 raters. You have the red, blue, and green curve, and you see that if you use a non-robust version, you take into account this single annotation provided by an isolated rater. While if you use a robust version, you can discard locally this rater, the red rater, but you can still use the rater at this part of the annotation. So we are also propose in this work some regularization of the output map and the possibility also to have several consensus segmentation and not a single one. So this is the baseline algorithm from which we compare ourselves, which is the seminal work of Simon Warfield and colleagues on continuous staple, which is based in their original paper was based on a Gaussian likelihood. So basically, it's a probabilistic model where the reference, which is T of n, so the performance of each rater is a noisy map of the reference segmentation, the consensus segmentation, which has been perturbed by a bias field here, and also by some global covariance matrix SYNAPI. And then you can perform the inference of both the consensus TN, the bias field, and the covariance matrix. So this approach has several limitations. First of all, there was a problem in the Rate bias estimation that was basically fixed by this author in 2016. And there is also the global estimation of performances, and not a local one. There were no regularization, and it was also assuming a single consensus. So we address this by replacing, in a few words, the Gaussian likelihood by a student T likelihood, which allows to actually have a spatially varying confidence map instead of being fixed for the whole map. We also added some generalized linear spatial prior, as I already presented before. This is to make sure that the consensus is smooth. And this is an example of this, for instance, a local, as I said, local performance estimation of raters. Here you see that for rater 3, you see that you have like a confidence map for rater 3. You see that you have a low value on this area corresponding to this part of the segmentation of rater 3. So therefore, you can see that the confidence map of a rater 3 is not a single value, but it's a spatially varying confidence. And also, you can use this approach for fusion of continuous map, not only to fuse segmentations provided by manual raters, but also to fuse the outputs of convolutional neural networks. So as an ensembling method. So we compare our ensembling method. This is on for 9 neural networks with the baseline algorithms, which are the majority voting and staple, and show that the approach was leading to, we believe, more robust, let's say again, ensembling of 9 different outputs of neural networks. So finally, we provided, I think it was the first time that we provided a way to generate multiple consensus segmentations. And this was done using, technically, we use the variational boosting, which means that you first estimate your consensus from one consensus, and then you see if you can better explain the data using some second additional consensus. And you do that as long as in your variational Bayesian approach, you have the mixture coefficient remains significantly large. And so at the end, what you have is you assume that each annotation given by an expert is actually a mixture from several consensus. So this is an example on this case. This is from, I forgot the name of this database. I guess it's LIDC, of lung nodules. It's a public database of lung nodules, where they have 9 different, sorry, this is a LIDC database, but it's the output of 9 different neural networks. And then you could see that in this case, the neural networks gave us different segmentation of the lung nodules. So we use we use cross-validation. That's why we have 9 different neural networks that were trained. And then using this approach, we were able to produce 3 different consensus. So the consensus, you see that they were all agreed basically for the main nodules, but there was a discrepancy according to these isolated nodules here on this part of image. Well, you see that one consensus, the red one, was ignoring this, while the blue consensus was including it largely, and the orange consensus was using only a small part of it. So I will just take the remaining 10 minutes to talk about the model-centric AI, focusing on a mixed supervision. So I already talked about the cost of annotations, but there is a grading of cost of annotations. So, for instance, asking the radiologist to outline a structure in the image, producing a segmentation mask test take a lot of time, while just providing a label. So this is here. So just providing a label to a single slice takes 1 second. So you see that there is a gradient of cost. So the manual segmentation mask being the high cost, then you have bounding box, and then you have landmarks, and finally you have labels. So the idea now is to cope with these varying annotation costs and to use those in the supervisions. So in this this slide summarizes the different types of supervisions for training algorithms to perform, in this case, the segmentation of cardiac MR images. So you can use weak annotations. So where you just provide, for instance, labels for the right and the left ventricles. In this case, you have weakly supervised learning. If you are using strong annotations, this is called supervised learning. And if you are mixing unlabeled images with strongly labeled images, this is more semi-supervised learning. And what we have explored more strongly is what we call the mixed supervised learning, which is a mixture of weak and strong annotations. And of course, you have unsupervised learning when you only deal with the absence of annotations. So in a mixed supervised learning, again, we explore this with this way of providing supervisions based on brain tumor segmentations, where we use again the BRATS database that you are probably familiar with, and where we ask radiologists, and actually in this case this was provided by the Grand Truth segmentations. So we have some images where we had full annotations, which is again the lesions segmentation mask. While there was also the idea of using weak annotations, which is just a label associated with each slice. So the slice says that whether there is a tumor which is present in the image or a tumor which is absent. Okay, so this is why we developed these combinations of full annotations and weak annotations, which we call mixed supervisions. And we could show in this case that by combining full annotations with more and more, you see that here you have increased performance when you add weak annotations with full annotations. But when you increase the number of full annotations, then the gain diminishes slowly. So for instance, when you use 30 fully annotation, there was no gain of actually adding weak labels. Of course, this depends on the way you design your mixed supervised algorithms. And in this case, what we did is that we added a second branch in this UNet segmentation neural networks. We add basically another branch to perform the weak annotations where we solve a classification problem. So this was also used in mixed supervision, was also developed in multiple instance learning. So for the supervision of whole slide imaging, so the idea here is that you need to specify whether this slide includes or not tumor cells. And the strong annotation, this is the weak annotation. So you know that only that the whole image includes weak annotations, and the strong annotations are the locations of tumor cells within the image. So in the case of whole slide imaging, the strong annotations are given on tiles. So the whole image is basically split into a number of tiles, and the tiles are classified into being tumors or non-tumors. So again, here we use a CLAM architecture for which we added supervision. And so for those of you who are familiar with this architecture, so we add supervision. Okay, so this is probably where it stopped here. Okay, this is the architecture that was improved by adding supervision on it. So there is a gain in terms of classification for the whole slide, as you can see here, but there is also mostly, you see that the gain in supervision for the whole slide, but the gain is mostly in terms of localization, in fact, of the tumor. So this is an example. So for the slide, this is a healthy slide. So therefore, you expect that all tiles in that constitute this slide have the same attention. And this is what is obtained by adding some supervision of the attention here. And here, this is a tumor slide where you see that the attention, thanks to supervision, a small amount of supervisions already provides a better localization of the attention mechanism. So attention is just a way of basically spreading the votes. If you want, each tile has a vote for classifying the whole slide, and the votes are weighted by this attention mechanism. And the most important, I think, aspect is this one. So this is an example, again, of a slide with tumor cells here, and without any supervision. You see that there's a lot of false positive. So which means that the multiple instance learning approach says that this is a tumor slice, but it says that it is for wrong reasons, because it thinks that all these parts of image is with actually tumor cells, which in fact the tumor cells are only in this part. So thanks to a little bit of supervision, actually we can have a much better interpretability and of classification, since now we know that the algorithms can properly outline the tumor cells in the image. So the gain here is not so much in terms of classification of the whole slide, but it's more into the interpretability of the results. So I would like just to finish, to specify, to list some other ways to deal with the problem of annotation. So of course you can use weak or no annotations. So you can do this by using self-supervision task, using secondary or pretext task in order to do some pre-training. You can use a pseudo-labeling approach where you assume that your algorithms is good enough to propose to distinguish between let's say good and bad examples of labels. You can use also, you can combine this with contrastive learning, while you expect some coherent impact of data augmentation. So these are the common ways to deal with semi-supervised learning. There is also another approach to minimize the annotation effort, which is to select the optimal data to be annotated. So this is called active learning, where you have an iterations between, you start by a small amount of training data that you increasingly improve by selecting the key examples that need to be annotated by the experts, and doing this into an active loop. Of course, another way to minimize this annotation efforts is to exploit the radiological reports. And now, in this case, the problem is to the structural nature of those reports. So we are collaborating with a group in a Paris hospital, at PHP, and then we are dealing with one example of reports that are unstructured, and which we try to use NLP tools to help extraction of automatically labels from that reports. And actually we failed to do this. It's way too complex, because this is really natural language, and you can use, I mean, I don't know about German, but French is very good at using double negations. And so it's really incredible incredibly difficult to exploit those reports. But then with another group, we use a fully structured radiological report, and this is very useful, and where we can actually exploit the localization of lesions in territories. We can use the volumes of the lesions in order to provide some weak annotations. And another way also to minimize the annotation effort is to use strong prior informations. So the prior can be into, for instance, the deep Bayesian networks, where you provide prior about the distributions of the weights. And we know that these techniques helps to better converge better with small data. You can use also some anatomical models. So this is example of a cochlear shape prior that we used in a recent model. And so this is for the anatomy, but you can use also this for physics, when you can use motion models, for instance, for the cardiac models, to constrain their analysis, to add more prior, and I think this is definitely a direction to go. So this, to conclude, I talk about the unsupervised quality control of image segmentation mask. I also mentioned about a way to fuse multiple annotations in order to measure the performance of algorithms. So this was based on a parametric consensus-based model. Well, you can also increase the number of consensus, so not only have a single consensus, but multiple ones. And I also mentioned the notion of generalized supervisions, not only to strong, but also there is a whole continuum between strong, weak, and no annotations. And I think this is the perspective, is to really have a continuum approach, which can be between the level of annotations. So there is an issue with accessing large databases, and this, I think we have a good hope that federated learning will help this, definitely. There is, I guess, a lack also of formalism about dealing with noisy labels and also multiple consensus. And I'd like also to cite some, I think one important perspective is to use unsupervised domain adaptation, which is, I think, needed also in many applications. And I will finish with this slide of Antibes in the April months, where you see both sunshine and snow for to ski neighboring ski resorts. And I'd like to acknowledge my colleagues here at TUM, also at the 3IA Institute of AI Institutes, and all the different partners, both academic, clinical, and industrial.